In 2017, astronomers detected something they'd never seen before. It came from outside our solar system, moving at speeds that shouldn't be possible, defying every explanation they could offer. Then it did something even stranger. It accelerated. And when scientists tried to explain it, they encountered a wall of silence, not from government agencies, but from the limitations of what we actually know about the universe. This is the story of Oumuamua, and why the most profound scientific mystery of the decade might be hiding in plain sight. For millennia, humanity looked up at the stars, wondering if we were alone in the cosmos. We built telescopes. We sent probes. We scanned the heavens for any sign of visitors from distant worlds. But we always assumed that visitors, if they came, would come from within our own solar system. We knew about asteroids. We understood comets and their behavior. We had cataloged thousands of objects in near-Earth space. We understood their origins, their behavior patterns, their trajectories. We had a framework. We had rules. We had mathematical models that predicted everything. And then Oumuamua arrived, and everything changed in ways we're still trying to comprehend today. On October 19th, 2017, a telescope in Hawaii spotted something impossible. The Pan-STARRS Observatory, designed specifically to scan the sky for dangerous asteroids and potential threats to Earth, caught a brief glimmer of reflected sunlight against the darkness. At first, astronomers thought they'd found a comet entering our solar system from the outer darkness beyond Neptune. Comets were common visitors arriving regularly from the frozen depths of interstellar space. They came from the Oort cloud, that vast frozen shell of icy bodies surrounding our sun like a cosmic shield. Billions of comets drift in that region, potential visitors waiting to be nudged into the inner solar system by passing stars or gravitational perturbations. But this object was different from anything they'd seen before. Within hours, calculations revealed something that made the astronomical community pause and reconsider everything. This wasn't a comet approaching us. It was leaving, and it had already passed through our solar system's closest point to the sun weeks earlier. We'd nearly missed it entirely. We'd almost been blind to the most significant interstellar visitor in recorded history. Astronomers around the world scrambled to observe this intruder before it vanished into the darkness of space forever. They named it Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. The name was poetic, carefully chosen to reflect the significance of the discovery, but the object itself was profoundly puzzling to every researcher who studied it. Using telescopes around the world, scientists rushed to gather every possible measurement before it disappeared beyond their reach. They coordinated observations across multiple continents and space telescopes. They shared data in real time. Every measurement raised new questions instead of providing answers. First, there was its trajectory, calculated with mathematical precision. The numbers suggested something unprecedented in all of astronomy. This object had originated from interstellar space, traveling between stars for millions of years before entering our cosmic neighborhood by chance. It was the first confirmed visitor from another star system ever detected. That alone would have been extraordinary enough to dominate scientific journals for decades. But Oumuamua wasn't finished surprising the astronomical community. When astronomers analyzed the light reflecting from its surface, they made an unsettling discovery. The brightness fluctuated dramatically, cycling in a pattern that suggested rotation. As it rotated through space, the reflections changed in ways that revealed something shocking about its shape. Most asteroids in our solar system are roughly spherical or irregular lumps, shaped by collision and gravitational forces over billions of years. Oumuamua appeared to be elongated, extremely elongated. The data suggested a ratio of length to width of at least 10 to 1, possibly as extreme as 20 to 1, or even higher than that. Some researchers described it as a cosmic cigar, narrow and stretched like a cylinder tumbling through space. Others called it a needle, or a rod, or pencil drifting through the void of space. Imagine a celestial object roughly 400 meters long, but only about 40 meters wide. A structure so thin and stretched that observing it directly would be nearly impossible unless light happened to catch it at just the right angle. Yet there it was, this impossibly slender visitor from the stars, defying the expectations of planetary scientists worldwide. The shape itself was strange, undoubtedly, but not necessarily physically impossible. Pancake-shaped asteroids and elongated objects exist in our solar system too. Scientists have cataloged asteroids with unusual proportions in distant regions, but combined with everything else astronomers learned about Oumuamua, the shape added to a mounting mystery that seemed to deepen with every new observation and measurement. Spectroscopic analysis revealed that the surface was unusually dark, darker than most known asteroids in our solar system. The infrared emissions suggested a composition unlike typical solar system bodies. Researchers detected hints of organic molecules on the surface, though the picture remained incomplete and frustratingly unclear. The object reflected light in ways that suggested a smooth, possibly metallic surface. This raised more questions than it answered. As more data accumulated from telescopes worldwide, The image of Oumuamua became increasingly strange and increasingly difficult to categorize within conventional frameworks of planetary science. The most perplexing discovery came from studying its trajectory with absolute mathematical precision and care. According to the laws of physics that govern celestial mechanics, Oumuamua should follow a predictable path through space. Gravity from the sun would bend its trajectory slightly as it passed through our solar neighborhood, but the amount of deflection should match astronomers' calculations exactly. Yet when scientists compared their predictions with actual observations, something was clearly wrong. The object was deviating from its expected path. It was accelerating outward, away from the sun. But there was no visible reason. No gas jets ejecting material into space, no cometary tail trailing behind it, no clear source of propulsion that any telescope could detect. Something was pushing this object, and nobody could identify what it was or where it came from. The acceleration was subtle, not dramatic or obvious to casual observation, perhaps only 5% more than expected, more than predicted. But it was consistent across multiple observations, it was measurable with mathematical certainty, and it violated the fundamental framework of conventional explanations that astronomers had relied on for centuries. If a comet was outgassing, gently pushing the object off its expected trajectory through space. But observations showed absolutely no coma around Oumuamua, no tail of gas or dust, no visible outgassing whatsoever. If it was releasing material, it was doing so without showing any of the telltale signs that astronomers had learned to recognize over centuries of observing comets. Astronomers faced a fundamental contradiction between theory and observation. The physics said something was accelerating this object away from the sun, but observation couldn't identify the mechanism. Within weeks, scientific papers flooded journals and preprint servers worldwide. Researchers around the world proposed explanation after explanation, each trying to solve the mystery. Perhaps exotic ices composed of unusual materials unknown to terrestrial chemistry were sublimating invisibly in the vacuum of space. Perhaps dust ejected from the surface at incredible velocities was producing a faint, nearly undetectable thrust pushing the object outward. Perhaps gravitational effects from passing through the sun's magnetosphere were stronger than anyone had calculated. Perhaps some combination of unknown factors was at work simultaneously. Each theory had significant problems. Each left gaps that observations couldn't fill. For most of the astronomical community, the answer lay somewhere in physics that was conventional but incomplete. The object was strange, undoubtedly. But strange didn't mean impossible. Perhaps better observations or new measurements would resolve the mystery in time. Perhaps we simply needed more data. But one scientist wouldn't accept conventional uncertainty and dismiss the possibility outright. Avi Loeb, chair of the astronomy department at Harvard University, published a paper that split the scientific community in half. His argument was bold, carefully constructed, and intellectually rigorous. What if Oumuamua wasn't just a visitor from another star system? What if it wasn't simply a naturally formed object shaped by cosmic processes over millions of years? What if the acceleration could be explained by a solar sail, a piece of technology designed to catch photons from stars and use radiation pressure as propulsion? A solar sail made from extremely thin material could appear metallic from certain angles of observation. Its darkness could be consistent with material specifically designed to absorb light rather than reflect it uselessly. The elongated shape could be consistent with a compact spacecraft architecture optimized for interstellar travel. The acceleration matched precisely what a solar sail would experience from radiation pressure from our sun. All the pieces of the puzzle fit together in a coherent and logical way. The response was immediate and dramatically polarized. Some scientists took Loeb's idea seriously and explored it further in their research. Others dismissed it as pseudoscientific speculation that damaged credibility in the field. Carl Sagan had famously said that extraordinary claims require extraordinary evidence. This certainly qualified as extraordinary. But the evidence, when examined closely, was circumstantial at best. The observation data fit multiple interpretations equally well. Different researchers could look at the same numbers and reach different conclusions. The acceleration was real and measurable, but the cause remained fundamentally unproven and unknowable with current data. Loeb wasn't claiming certainty or absolute proof. He was claiming that among multiple possible explanations, the artificial hypothesis deserved serious consideration instead of immediate dismissal. That argument itself became controversial. In academic science, suggesting an object might be artificial carries enormous intellectual weight. It invites intense skepticism from peers. It demands perfection in reasoning and evidence. Even perfectly presented, such ideas face an uphill battle in the scientific establishment. What emerged from the scientific literature was a complex, nuanced picture of genuine uncertainty. The basic facts were these. Oumuamua arrived from interstellar space with no propulsion system visible to our telescopes. Its shape was unusual, but not physically impossible for a naturally formed object. Its acceleration was small but measurable and consistent across multiple observations. Its surface was dark and possibly reflective of light in unusual ways. No outgassing was detected despite the acceleration observed. These were the confirmed data points. Everything else was inference and interpretation. Loeb's solar sail hypothesis was internally consistent, but so were natural explanations involving exotic ices or unknown sublimation mechanisms. The truth was that multiple explanations fit the available data equally well. Science advances by eliminating possibilities until one remains. But with Oumuamua, scientists couldn't eliminate enough possibilities. They simply didn't have sufficient information to settle the debate definitively. Critics of the artificial hypothesis raised important points that deserved serious consideration. The object had apparently traveled through interstellar space for millions of years, possibly billions. No technology that humanity has ever created could withstand such a journey unscathed. Cosmic radiation would have degraded any materials we understand. Impacts with microscopic particles and dust would have accumulated damage over eons. Unless the technology was far more advanced than anything humanity has imagined, how could it possibly survive the journey through space? Moreover, if an advanced civilization had deliberately sent Oumuamua through space, why design it this way? Why make it a thin, barely visible object? Why not send a probe with visible instruments and clear markers of artificial origin? If the goal was to be noticed and recognized, Oumuamua seemed like an inefficient choice for first contact. The natural explanations had their own problems that scientists couldn't ignore or dismiss easily. Outgassing without a visible coma seemed unlikely, but wasn't absolutely impossible in all circumstances. Exotic ices might sublimate differently than terrestrial ices behave under different space conditions. Dust ejected from the surface might not create the visual signatures astronomers expected. There were mechanisms that could explain the acceleration without requiring artificial propulsion, but many of these mechanisms required assumptions about Oumuamua's composition that couldn't be verified with current technology. Scientists couldn't send a probe to intercept it. They couldn't land instruments on the surface. They couldn't analyze material samples. They couldn't conduct any hands-on investigation. All they had were remote observations from Earth and space telescopes. Those observations had definite limits. Multiple theories could survive with the data available to them. The deeper issue wasn't about Oumuamua specifically. It was about the fundamental limits of astronomical science itself. Space is vast beyond human comprehension. A visitor from another star system arriving without any advance warning, with limited time to observe and with technological constraints that prevented detailed investigation. This was a unique situation in the history of astronomy. Every object astronomers had previously studied was either in our solar system and reachable for detailed observation, or a distant star whose properties could be inferred through decades of careful study. Oumuamua was a brief visitor on a defined trajectory, accelerating through our cosmic neighborhood before vanishing forever into space. Scientists had one chance to collect data, and that data, while intriguing, wasn't complete enough to settle the mystery definitively. Scientists eventually reached a consensus that reflected both genuine mystery and scientific caution. Oumuamua was unusual and remarkable. Its properties required explanation. The acceleration was real and demanded a physical cause. But the evidence didn't definitively prove any single explanation beyond doubt. The artificial hypothesis, while theoretically possible, remained speculative without additional data. The natural explanations, while having significant problems, weren't definitively ruled out by observations. This wasn't the scientific community being deliberately evasive or hiding information from the public. It was science being honest about uncertainty. Real science doesn't claim certainty when genuine uncertainty exists. That honesty, while scientifically appropriate and intellectually sound, sometimes sounds like silence to those hoping for dramatic answers. What made Oumuamua truly significant wasn't the object itself, though that was remarkable. What mattered was what its discovery implied about the universe and our understanding of it. Astronomers could now calculate statistically how many interstellar objects like Oumuamua might be drifting through the galaxy. Some estimates suggested that if one object this size entered our solar system every few decades, then our galaxy might contain trillions of these visitors. We'd always assumed we understood solar system visitors completely. We calculated their origins, predicted their paths with precision, and understood their physics. Oumuamua revealed that the universe was more complex and less understood than our models suggested. It was a humbling reminder that space might contain objects unlike anything in human experience. The object continued its endless journey outward, moving beyond the orbit of Neptune, beyond the Oort cloud of icy bodies, back into interstellar space. Telescopes tracked it for months, collecting every possible bit of data before the signal became too faint. Then it passed beyond our technological reach. Scientists archived the data and moved on to other mysteries. Oumuamua became a famous unsolved case, discussed in astronomy classrooms and around dinner tables, but not a priority for active research. It was gone, and there was nothing humanity could do to follow it or learn more, or so everyone believed for a time. In 2021, scientists announced Project Lyra. This was a conceptual study, not yet a funded mission, but it represented something profound and forward-thinking. If humanity built a spacecraft with sufficiently advanced propulsion, could we intercept Oumuamua? The answer was surprisingly affirmative. It would require nuclear fusion engines or similar advanced technology that's still theoretical. It would take approximately 75 years to reach Oumuamua and match its velocity. The spacecraft would need to be fully autonomous and survive the journey through interstellar space. But physically and mathematically, it was possible. Humanity couldn't reach it immediately, but perhaps our descendants could within generations. The announcement was significant. Whether Oumuamua was natural or artificial, we were developing the capability to investigate such objects. Technology that today existed only in theoretical papers might become reality within generations. This possibility changed the entire conversation around Oumuamua fundamentally. Scientists began discussing a future where interstellar investigation was achievable and practical. They considered what a spacecraft might find when it reached Oumuamua, assuming Lyra or a similar project was eventually funded and constructed. If the object was artificial, what would decades of detailed study reveal about its creators? If it was natural, what could up-close examination tell us about formation processes in other star systems? The discussion shifted from debating what Oumuamua was to planning how we might learn what it actually is. That represented real progress, however distant the actual investigation might be. Javi Loeb continued publishing research on Oumuamua and its broader implications for science and society. He wrote a book titled Extraterrestrial that explored the possibility of artificial origin in considerable depth. The book attracted significant attention and equally significant criticism. Some reviewers praised his willingness to consider unconventional hypotheses seriously. Others accused him of promoting pseudoscience and damaging the credibility of serious astronomy. Loeb's career was affected by his advocacy for the artificial hypothesis, though he maintained his position at Harvard and continued his research. The controversy around him illustrated something important about how science actually works. Scientists are not immune to social pressure and career consequences. Proposing certain ideas carries professional risks. Suggesting artificial origin for any object attracts intense scrutiny that conventional hypotheses don't face. This isn't necessarily wrong. Extraordinary claims do deserve extraordinary scrutiny, but it does mean that some questions get explored less thoroughly than others. The scientific silence around Oumuamua wasn't conspiracy or cover-up by any government agency. It was something more subtle and more complex. It was the normal operation of scientific institutions, facing genuine uncertainty and ambiguity. When a mystery can't be solved with available data and tools, scientists eventually move forward with limited attention. They allocate funding to researchable questions, where answers seem achievable. They focus on problems where progress seems possible. Oumuamua would remain mysterious until new observations or revolutionary technology revealed more. Continued speculation without new data wouldn't advance understanding. So the attention shifted gradually. Oumuamua became a historical note, an interesting case study in the limits of astronomical observation and human knowledge. But the implications lingered in the minds of serious researchers and thinkers worldwide. If an interstellar visitor arrived that scientists couldn't definitively categorize with certainty, that raised profound questions about the universe. How many such visitors had arrived previously before telescopes existed? How many might arrive in the future? What did humanity's inability to identify Oumuamua's nature tell us about our understanding of the universe? These weren't questions with immediate answers. They were questions that would occupy astronomers for years to come, driving research and investigation forward. The true mystery of Oumuamua wasn't whether it was artificial or natural. It was what its arrival told us about space and our place within it. For centuries, humans thought of our solar system as isolated and separate from the rest of the cosmos. We knew other stars existed distantly, but they seemed remote and separate from us. Oumuamua proved that objects could travel between star systems regularly. It proved that our neighborhood wasn't as isolated as we believed. If objects could come here from other stars, could we send objects to other stars? Could advanced civilizations do what we're only beginning to theorize? These questions elevated Oumuamua from an astronomical curiosity to a philosophical challenge to our understanding of everything. The object represented a boundary line between knowledge and mystery. On one side was the known universe, understood through our observations and theories. On the other side was everything we didn't know, everything beyond our technological reach and theoretical framework. Oumuamua sat on that boundary, visible but not fully understood, real but not fully explained. It embodied a profound truth about science and knowledge. Despite all our knowledge, despite our telescopes and calculations and centuries of study, the universe remains mysterious. We understand vast amounts, but vast amounts remain unknown and unexplored. Objects like Oumuamua remind us of that gap between knowledge and ignorance. They remind us that wonder is still possible, that mysteries still exist, that the universe hasn't given up all its secrets. Future discoveries would likely provide context and understanding for Oumuamua. Astronomers expected to find more interstellar visitors in coming decades as technology improved. Each new visitor would add to our understanding of interstellar travel and composition. Each would either confirm that Oumuamua was typical or reveal it as unique. If many similar objects arrived, their properties might help explain Oumuamua's characteristics. If Oumuamua remained unique, that uniqueness itself would be scientifically significant. Either way, time and advancing technology would eventually provide answers. The silence around Oumuamua wasn't permanent. It was the silence of scientists admitting honestly that some questions required patience, that not everything could be solved immediately, that mysteries had value even when unresolved. What made Oumuamua truly revolutionary was this simple fact. It changed how astronomers thought about their field and their mission. It revealed that the solar system, our cosmic home, was more open to visitors than anyone had calculated or predicted. It demonstrated the limits of current technology in investigating such visitors thoroughly. It proved that a small object could carry enormous questions that challenge our understanding. And it showed that science, at its best, was honest enough to say, we don't know, we can't determine this yet, but we'll keep looking and searching for answers. The questions Oumuamua raised would persist for decades to come. The answers would come slowly, if at all. But the asking itself mattered profoundly to human progress and understanding. As you look up at the night sky tonight, understand that space isn't empty and sterile. Visitors travel between stars constantly. Objects we don't understand drift through the cosmic dark. Most will never reach us. Some will arrive without warning and vanish before we fully understand them. Oumuamua was one such object. It came from another star, passed through our solar system, and continued its journey into infinity. Scientists studied it carefully. They debated its nature openly and honestly. They admitted uncertainty when certainty wasn't possible. That admission wasn't weakness. It was the strength of a scientific process that values truth over convenient answers. Oumuamua remains a mystery. And mysteries in science and in life remind us that the universe is larger, stranger, and more wonderful than we typically imagine. It passed through our cosmic neighborhood only once. It will never return. But it changed how we see the sky forever.